only going to get through about the first 9 pages or so of this, and then they'll give you a couple more to work, similar to what I'll go through. So we might have to come back for the integrated rate law, but we'll see how far we get. I'm going to try to do this with some back and forth for you guys. I know it's only 2 of you, so we'll see how that goes. First of all, kinetics. What does that make you think of?
Energy.
Energy, okay. So kinetic energy, what is that? Energy of?
Movement.
As opposed to potential energy. How would kinetic be different?
Was it potential like stored energy?
Yes.
Kinetic energy is like, I want to say transferred?
Yeah, it's moving. It's energy of motion. So we can actually do calculations of that motion. A hint for that is there's signs all along the roads and the highways with different rates on them. Do what I'm referring to there?
The miles per hour?
The miles per hour. So a rate is a distance divided by a time. It's some change in some quantity over time. For us, we're going to have brackets. Do you remember what brackets mean in chemistry?
Of course.
Concentration. So in that case, it'd be the change in concentration of whatever chemical I'm representing with A per time. Okay, so that's the first sentence here. Second sentence, it says thermodynamically favorable. That is the new terminology. It's what we prefer for students to use on test. It used to be called spontaneous or spontaneity. We don't like to use that term anymore because it gave people the idea that it was referring specifically to speed, or that in the sense that it meant that it would happen fast. But it's not the same thing. Thermodynamically favorable just means it's going to happen. It's not necessarily spontaneous in that it just happens all at once. Although having said that, we typically look at initial rates and not what happens much later in the reaction, just because that's easier in first year chemistry. Okay. So again, it does not imply a rapid rate. It is just favorable. I mean, it's going to happen. The reaction is going to go that direction. Okay. For example, diamond into graphite. It can happen. It is thermodynamically favored, but it's very slow. It wouldn't be very good if diamond rings were to very rapidly go through that reaction to become graphite. It's still thermodynamically favored. It's going to happen. It might take hundreds of thousands, millions, billions, whatever years, but it's more than our lifetime. So thermodynamically favored does not mean it's just happening right away. It has to do with activation energy. We have to have activation energy or energy of activation. We'll usually put A as a subscript for that. And it has to do with a lot of things going on within the chemicals themselves and how the chemicals are reacting with one another. So we'll look at some of those things today. So what factors affect reaction rates? Some of these you already know. We've talked about some of them, such as down here. I'll get to it in a moment. Number 3 with temperature, we talked about last time. But let's start off with the nature of the reactants. Some reactants react in a hurry. Some do it slowly. Wow, what's the difference? Well, a lot of times it has to do with the state of the reactants. For example, gasoline. Compare gasoline in the liquid state and the gaseous state. The liquid gasoline, although it is combustible, is not nearly so much as the gaseous state of gasoline. As a matter of fact, it's kind of a stupid game, but I've heard of people throwing matches into liquid gasoline and trying to throw it fast enough that it doesn't catch on fire. That's a dangerous game because that gas hovering at the top is likely to catch on fire and even explode. But if it does go in that liquid fast enough, it might not even light the liquid on fire. The liquid molecules are moving so much slower. The gaseous molecules moving so much faster. So again, rate, the speed of those molecules moving around. Here's another example. Let's say we take 2 solid crystals and just slam them into one another. What happens? Well, probably nothing. But if we take and dissolve them in water, now those molecules and those ions are moving around and hitting one another at a much more rapid rate and with more changes in things like their orientation so that they can break bonds and form bonds. Another idea is their chemical identity. So what is going on within that molecule itself? What about the bonds? For example, if it has more bonds, that means that molecule is held together tighter, and therefore it's going to have a slower reaction rate. So a double bond between two atoms is going to be harder to break than a single bond. Triple bonds could be even harder to break. We did that in class where I took two hydrogens and stuck them together, two oxygens and stuck them together, and two nitrogens and stuck them together. And we found that this triple bond was harder for people to pull apart. So the chemical identity, the nature of the molecules or ions themselves has an effect. We can sometimes use the periodic table to look at this. For example, sodium and calcium. Where's the periodic table? So sodium and calcium, which one is more reactive? Or we can go back to other things we talked about back in that unit, but sodium is probably a lot more reactive. It's even the example we saw threw into the river where it made a huge explosion of water everywhere. Calcium, if we were doing labs right now, you'd see just make a few little bubbles. It'd still be reactive, but not nearly as reactive as sodium. So the nature of the molecules, in this case, the electron, size of the atom, those sort of properties. Photosynthesis is one we can relate. Photosynthesis is slow, but it is thermodynamically favorable. We'll also talk about catalysts in this section. What do catalysts do to reactions?
They lower the activation energy.
Lower the activation energy and therefore
speed up the reaction.
Speed up the reaction. And in biology, we talked about some of those. We'll look at some of that a little bit more in the future. Those were proteins, or what's another word for catalyst protein? Enzymes. Okay. So another thing, so we looked at the nature up there. Now let's look at the concentration of reactants. You could probably guess that if you have more gasoline, you're going to have a bigger fire. And that's generally the case. It's not always the case, but it's generally the case. Let's relate this to the hallway at school. The hallway right now is empty. There's very few people walking around, maybe a custodian or a maintenance worker. So there's probably going to be very few collisions. But let's say we have more students in the hallway. So when school starts back, we've got more students in the hallway. Then compared to right now, I would expect there to be more collisions. So more students, more collisions. Well, more reactants, more collisions, therefore more reaction and a faster reaction rate. Well, how else can we change that? What else can we change about the students besides the number of students in the hallway? We can change their speed.
Yeah.
Faster students in the hall is going to mean more collisions. So the faster those molecules are moving, the more likely they're going to collide. And we can also talk about the size and shape and if they're swinging their keys around. So it comes back to the nature of molecules like we talked up here as well. Oh, sorry, this is off the screen. Let me get rid of my notepad. And the faster it gets into the next part, temperature. As we said last time, heat them up, speed them up. And it doesn't take very much heat, as we'll see in just a moment, for that to happen. Well, why does heating them up increase the reaction? Because they're moving faster, and if they're moving faster, they're more likely to collide. And when they collide, the collisions are going to be more energetic. But increase in temperature produces more successful collisions that are able to overcome the needed activation energy, as we mentioned earlier. And you want to start remembering activation energy, that's where we're looking at graphs like this, like the reactants and the products. And we've got to overcome this amount of energy for the reaction to take place.
Yeah.
An increase, and this is a general rule, not a law, but a general rule, if we increase the temperature by 10 degrees, sorry, I'm off the screen again, then that's going to double the reaction rate. Not a steadfast rule, but it is fairly common that just a very small increase in temperature is going to increase the reaction rate. And as we said before, it's dependent with the activation energy. Let's see. Oh, I should back up, although we'll come back to it again with collisions. Collision theory we covered in honors. There's a couple of things that have to happen. One, we have to have the right geometry. So they have to be in the correct orientation, so they hit each other where whatever it is needs to be broken, or whatever it is needs to be formed in order for that reaction to take place. And it needs to happen with enough energy, sufficient energy for the reaction to take place. And if we have both or either of those, then we could have effective collisions. And that's some terminology potentially to throw around on the AP test. So we've looked so far at the nature of the reactants, concentration of the reactants, and temperature. Any questions so far?
No.
Okay. Well, the next one is the surface area. If we have more exposed surface, then there's more that can react, and therefore that can affect the speed. And we've done this in the lab where we've ground things up. It affects the chemical reaction speed. It also, in the case of one of our labs, affects the physical evaporation rate. The water was more exposed to be able to evaporate. Let's see. What I talked about. Okay, so in the gaseous state, if we come back up here to the gasoline earlier, in the gaseous state, it's bumping into molecules more often, so it's reacting more, but in the liquid state less. We don't really have solid gasoline, which you could imagine if it was, then it would react even less. Well, if we're doing with a solid substance, we can increase its reaction rate by grinding it into a powder, somehow making more of its surface exposed. So therefore, there's more boundary, more interfaces, more places for things to encounter each other or other things in a reaction. When I taught in California, our local town had a grain elevator. Grain elevators may have explosions. This is something they have to be very careful about, because as this grain is getting ground up into smaller size, going along conveyor belts and stuff, this powder will be so fine in the air that just a spark from a fan turning on could be enough to blow the entire building up. Even though you wouldn't normally think about flour as being reactive. Matter of fact, if you had a fire on your kitchen, you might throw flour on it to put the grease fire out. But if it's in a high enough concentration and the right ratio with oxygen in the air, it will actually cause a fire. This is something you can do very easily with like a 6 to 8 inch piece of PVC about your height. Put a candle in the bottom of it and drop some about a tablespoon or so of flour in it, and you'll get a poof. It'll burn and cause a little bit of smoke and powder to come out the top of it. If we were in class, we had a grain elevator demonstration with a paint can we were going to do. Another one relative to that that we would do is the alcohol, rubbing alcohol in the cannons, where you would squirt just a little bit, 2 milliliters into the cannon, and we'd mix it up for 2 minutes. We'd shake that thing around, flip it, twist it, everything to get that gasoline, or sorry, not gasoline in that case, alcohol distributed so it would be more spread out, right ratio to the oxygen to cause the ignition to launch our cannon. Let's see. Okay, I don't think I have anything else to talk about there. I taught in Virginia. I didn't teach in West Virginia, where I was at Northern Virginia. There weren't any coal mines, but if there are coal mines, that's something to be very careful of, because that dust from the coal mining can get in the air, and again, very slight spark, a little bit of activation energy there can blow the whole mine up. So if we've got a lot of surface area, we're going to have more thermodynamically favored chemical reactions. The way we generally do it, though, in chemistry is with solutions in water, so that they're able to float around, move around, and hit each other. Speaking of the coal dust, again, coming back to like those crystals that we talked about earlier, if it were just two pieces of graphite or two pieces of charcoal and you slam those together, you're not going to get a reaction. Matter of fact, backyard barbecue, whoever's starting the fire is probably actually going to use some type of fluid to accelerate that fire to get it started. It's very hard to get the coal itself to start naturally, even if it's charred coal, which is even easier to get started. And you can look at the grain size with that. If you take a piece of charcoal and try to write on paper, it will, in fact, write on paper. It'll come off in sheets, kind of like graphite.
Okay.
Any questions or comments on the first page?
No, that's good.
Okay, let me look over my notes, see if anything. I think I covered everything. Okay. Next, well, what if we add an inert gas? If you can read here, you can see it has no effect. Why does it have no effect? It's inert. Adding an inert gas, one of the halogens, for example, isn't going to affect the reaction rate. That's a trick question that the AP exam often likes to ask. There's not going to be any effect based on that reaction with that inert gas. Now, we could talk about equilibrium. I don't really want to get into that here, but you may remember we talked about pressure with equilibrium, where we were doing that in the past. But be careful not to confuse the two, although there will be some similarities here. Okay, I think I jumped again a little bit with catalyst. Catalyst in biology are those proteins or enzymes. They're likely to speed up chemical reaction. Here that is here. And they may do that because of many different ways. They may act like the enzymes you talked about in chemistry, that lock and key model where they get into whatever place. But if you've ever been in a band or a play or anything where you've had a director, that director is kind of like that catalyst. It's not actually part of the play or part of the band performance, but he or she is guiding the reaction, making the molecules go the direction they're supposed to go. In the case of this, making them collide with the orientation they're to collide. If two actors in a play are supposed to do a high five, well, the director is going to have them facing each other probably to do that high five. Same thing with the molecules. The parts that are going to react need to be facing each other when they collide into one another, and catalysts can help do that. This also relates back to IMFs and molecular forces. We talked about that with just walking down the hall. They're more likely to hit each other if they're moving faster, but if they're moving slower, they're more likely to stick to one another. So all of these things are relative to each other. And although we generally do this on paper, the three-dimensional shape is important as far as what site it hits or part it hits, or if it's even turned that way or not. So John already answered this, how do catalysts do this? They lower the activation energy. So we'll take that type of graph we had before, like this. And what they do is change this to something like this. Now, we'll come back to this a little bit in a moment, but note that this can go either way. Lowering this activation energy lowers the energy for products to come reactants, as well as reactants to come to products. And that's that equilibrium piece that we were talking about previously. Another thing to remember is catalyst is not part of the chemical reaction. So if we have a chemical reaction, we're going to write that catalyst generally above the arrow. That does not necessarily mean that it won't be part of our equilibrium expression, because it could be part of the rate determining step, which is the slowest step. The slowest part on the highway determines the speed of the cars on the highway. If there's a traffic jam, it's going to slow everybody down. Okay, they can be heterogeneous, homogeneous. We're getting a little bit in the woods here. Let's skip to this. The forward and reverse reactions. So this can go this way, or it can go this way. And this part at the top, by the way, this is called the activated complex. We'll come back to that in a moment as well. H2O2, what is that?
Hydrogen peroxide.
Hydrogen peroxide. So let's say for whatever reason, you need to send a little kid that can't read to go get the hydrogen peroxide. You're dealing with another sibling or somebody that's got a cut and you want to put hydrogen peroxide on it. So send this child that can't read into the bathroom to get hydrogen peroxide. And in there, you know, there's rubbing alcohol and there's hydrogen peroxide. How might you tell this person to get the hydrogen peroxide? How might the bottles look different?
H2O2, it's like brown, right?
There'll be a brown bottle. Why is there a brown bottle for the H2O2? Why is it not clear? Well, what's brown going to change? It's going to limit the amount of light that can get into it. And that's important because light can break that down into water and oxygen, which is not what we want. We want a greater amount of hydrogen peroxide if it's something we want to use. And we don't want that oxygen there. Could mean that there could be a danger of potential explosion or something, not generally in your household bathroom, but it is something to consider. The one I had on my desk before we left, you might remember, was kind of accordion shaped. Mm-hmm. So if that breakdown did occur, that bottle would expand rather than explode. In household concentrations, that's not a concern, but in the type that we would have used in the lab, we'd have done the elephant toothpaste lab. Sorry, you guys are missing a lot of fun demos. That would have been a concern with that concentration. And again, with the catalyst, and talking about if they're homogeneous or heterogeneous, homogeneous catalysts actually appear in the rate law, which we'll be dealing with some of that later. It's not something you generally got to figure out, though. Again, we're kind of getting into the woods here a little bit. See if I missed anything. With a catalyst, I should say they're not used up. You get them back at the end of the reaction. So if some process requires platinum, although that is extremely expensive, it's not really a concern because it's going to settle out usually as a precipitate, and you can reuse it the next time you run that reaction. Okay, questions or comments so far? Okay, next is collision theory. I say next, although I think I've pretty well covered it already. I did not mention specifically, though, Coulomb attractions. Do you remember what that is?
Yeah, the force of attraction.
Force of attraction, dealing with those opposites attract, positive and negative attract. The more positive and the more negative, the more difference in charges, the more attraction they have. And this is related when you take physics on the same type of way that gravity is with mass instead of charge. Let's see. Okay, there's the successful collision terminology I said previously. You might want to mention if you got a question like this on the exam. There's an example in black and white. It's kind of hard to see though. So unless there's no questions, we'll move on to the next page.
That looks good.
Okay, next. Actually, more of the same. Particles must collide. That's collision theory. One at a time. Proper orientation. I think I already mentioned all of this. Effective collisions. Term again. Okay, the activated complex I mentioned previously. In that case, would be this. And again, it can go either way. We are generally looking at the forward reaction. That's what we want to take place as chemists to get whatever product or products we want, or in some cases, to get rid of the reactants. Another thing I didn't mention, though, is the vibrational energy. So it's not just that they collide, they need to collide with enough energy, the correct amount of energy, the electrons vibrating such that they're going to be knocked off of or onto whatever is happening. So again, it's down to enough energy no matter what we're talking about there. Okay, that's the basics of what we've covered so far. Here is something that is kind of new to the AP exam, at least since revision before last, or maybe last revision, and that's the Maxwell Boltzmann distribution. Not something I did a whole lot in college until P-Chem, but it's been brought down to first year Chem a lot because it helps to explain what's going on. So let's kind of relate it to what we just talked about. So with the reaction process here, we're talking about potential energy on this side and the direction of the reaction. Well, what determines that progression? Well, partly the rate of the reaction. Let's see what I had here previously. So if we look at this equation we had earlier, what are two things that are important for the reaction if we want to model this rate? Concentration and time. Concentration over time specifically. Well, that's what this distribution represents. This is the number of particles, the concentration. To go back to the hallway example, on this left-hand side, let's say we have more students. So this is the number of students. And on this side down here, let's say we have faster students. That's related to the energy of the student. So we got the first situation where there's some students in the hallway, and then now students in a hurry, the bell's about to ring, so they're moving faster down here. What happens? Well, we had this initial T1, this high curve that fell down right down here. We had like this number of collisions with students. But after we speed this up, notice the shift. It shifts to the right. There's more energy. Also, it drops. That means there's a lower percent. Before with T1, a greater amount was over here, the median. Over here, now it shifted because they're moving faster, so now there can be more collisions. Those collisions before plus these extra collisions. Well, we talked about before that we could double the reaction by simply increasing by 10 degrees. This is about what 10 degrees does. It doubles the amount of the reaction. The rate of reaction doubles just by that little bit of increase in temperature. Related to the hallway, teachers yelling at the students to slow down so we don't get these collisions. So now, types of chemical reaction rates. Instantaneous we're going to look at. We'll also look at relative rates, differential rate law, and we are probably not going to get to on like page 12 or something here. But much further down in here, we'll get to the integrated rate law. I doubt we'll get there today, though. So let's start out with rate laws in general and instantaneous rates specifically. So rate is a change in something over time, distance over time for speed, or in this case, concentration of reactants over time. Well, what was concentration again? That's molarity. What are the units for molarity?
Moles per liter.
Mole per liter. Okay. We might also see this sometimes written as mole liter to the -1, just the inverse. They oftentimes type that on things like the test, so just don't let that confuse you. You might also see second to the -1 if it's a speed like meter per second. That'd be meter second -1. Okay, so reaction rates. So what is happening with a reaction? Well, let's look at this. Here is our concentration. And over here is our time, in case you can't read those graphs. We have different substances here. Here is NO2. And then over here, we have a couple of different other substances. Well, what can you tell me about NO2 based on this graph? What is it? Is it a reactant or a product?
It's a reactant.
It's a reactant. How do we know that? Because there's the concentration of it. What's the initial concentration of these other two?
0.
0. So those are our products. So it makes sense we got a positive slope for them. There's an increasing amount of products as this reaction occurs. And therefore, for the reactants, there is a negative slope, a decreasing amount of those. So as the reaction continues, and if we're writing a rate expression, we would show this because the reactants would be disappearing and the products would be appearing. Well, how do we show that in an expression, a mathematical expression? Negative for the reactants disappearing, positive for the products appearing. So what is the reaction for this particular graph or set of data? Well, we've got NO2 here. We've identified that as the reactant, so we can write NO2. And these other two things must be products, NO and O2. What else do we need to do?
You got to balance it.
We've got to balance it. Easy way to do that is we got 3 here and 2 here. Well, we can't do that. We need to make them both even or both odd or whatever. In this case, I'm going to make them both even. So that's 2 and 4, 2 and 4, 2 and 4. So the way you're going to see problems like this is generally with a data set that you're going to have to interpret or with a graph that you're going to have to interpret. We will look at potentially graphing some of these later, but I'm thinking that with the test being so short this year that they're probably going to either give you data or they're probably going to have another type of reaction that we'll look at where we can compare specific things and not have to do the whole thing in a graphing calculator. I'm thinking that they're going to think that would slow people down too much and not really show understanding. As a matter of fact, I've heard from some teachers, although not from Trevor, that the math is probably only going to be like 25% of the test this year. Okay, so we're talking about types of reaction rates. Instantaneous is our first one. Well, instantaneous simply means what it means is in an instant. In an instant of time, what is happening? So, John, you're in calculus right now, right?
I was last semester.
Oh, last semester. Okay, you've had calculus. So some of this you can use calculus for. We're not going to in this class, but you'll recognize some of the terms already then. So let's look at an instant of time. We've already got something graphed right here. So let's look at that instant of time at 100 seconds. I think that's seconds. So at that time, what's going on? Well, how do we find out the instantaneous? Well, in trigonometry and calculus, you probably call this the tangent to the curve. Be careful with that in here, although that is what you're doing. We aren't going to get any points on the AP exam for saying tangent to the curve. Well, how do we do that? What is this and this then? Back to geometry, probably middle school.
Right triangle.
Okay, it's the right triangle. And it allows us to calculate that slope by doing rise over run. Well, what is rise over run? Well, in this case, it's the change in the concentration of NO2 over the change in time. So the slope of this is the rate, specifically the instantaneous rate. And we could also do that down here for these other two reactants. You can see they did it at another point in time, 250, I think that is seconds. We could figure out instantaneous rates at any point along any of these curves just by taking the rise over the run. And we can approximate that on the graph. You can see here that it's like they pulled where these 2 points are on the graph. Or if we're given data, we can pick points, or if they give us specific time intervals they want us to check, we can use those intervals to find out what that instantaneous rate is. Well, what's happening to this NO2 as the reaction progresses?
It's decomposing.
Okay, it's decomposing, its concentration is decreasing. What's happening to these others? They are forming, their concentration is increasing. So it makes sense that they have a positive slope. Again, back to this, reactants disappear and products appear. I keep referencing some things in here because they might be terminology that you need to mention as you're discussing, and I do expect that you're probably going to discuss this. Okay, so instantaneous rate, I used that earlier, but you can do any of them. A hint here. What is our x-axis on this?
Time.
Time. If your x-axis is time, that is a big hint. That is a hint that you are dealing with rate.
Yeah.
If you're in a math class, a physics class, calculus class, time is down there, that's a rate. We're never going to have time up here. We're not time travelers. Okay, instantaneous. Okay, I'm not going to practice all of this down here at the bottom with you, but let's just look in general at what's happening, say at approximately 10 seconds. I'm going to kind of fudge here and say 10 seconds is about right there. Well, what is the instantaneous rate for this substance, whatever this substance is? Well, right here, I'd say that's probably about 25, and that's 50. So what's the instantaneous rate there? 25 divided by 10.
Yep. It's about 2.5.
Okay, so that one's about 2.5. Now, let's look again, approximately. I'm not really doing the tangent to the curve here. For this forming. Well, again, we got 10 there, and here we got 25. So what's this one?
Same.
They're both 2.5, but what's the difference? There's a very important difference here.
The red should probably be negative.
Yes, this is negative. These are disappearing, and these are forming. Be careful about that. That sign can be very important.
Gotcha.
Let me back up just a second. I got my papers out of order. Okay, so this substance up here, what is happening to it? You told me earlier with the NO2.
It's being used up, right?
Being used up, it's breaking apart, it's decomposing. So let's relate that back to first year. Well, this represents a bond. So in order for reactions to occur, we have to break bonds. And then down here, in that purple region, we're forming bonds. Well, a breaking bond requires energy. Forming bonds releases energy, and you heard that in that snap. So that's just a little manipulative there for you to relate the two with. Okay, your next page. Let's see, we're on number 2. I got my pages right. Is that where we are?
Yeah, that's right.
Yes, page 5. Okay. Okay, next, well, first we talked about instantaneous reaction rates. Now we're going to talk about relative reaction rates. So relative to each other. So as the rate of one thing, the rate of the other thing. As the rate of the reactant versus the rate of the product. Reactant being negative, product being positive, as we mentioned before. So here's the reaction we just dealt with, and we really kind of went pretty depth into this, in that the NO2 is going away and these were being formed. We can actually do calculations with this. I didn't write this down, so give me a moment, we'll go through this. Let's see. Okay, here's a little hint as to how to do these. Let's just take the reaction. I don't know where I left my notes here. Here. And the simplest way to do this is to take each coefficient and say 1 divided by it. So we had 2 of the NO2, now we have 1/2 here. And it's going away, so we have negative. This was 1, so 1 over 1, well, it cancels, or it's just 1, and it's positive because it's product. Here we have 2, 1 over 2, that's 1/2. So 1/2 for those. If you want to write 1 over 1 here, you could, but they wouldn't need to see anything like that. So that's the initial rate of the reaction. For relative rates, all we're doing is comparing one substance to another and another substance to another. We're comparing all of them to everything. No matter how many the things are, we want to relate them to one another. So you have to have, as we referred to before, that balanced reaction. You've taken 1 divided by that coefficient for each one of them, and then you can write it in a reaction rate like this. The change in concentration of whatever that is over time, or the change in concentration, whatever that is over time. Notice in between all of these are equal signs.
Okay.
These are related to one another. Okay? That's why those coefficients are different numbers. Okay? And you might want to, instead of using fractions, use whole numbers. If you're doing that, these would be your numbers. So we'd have to multiply all these something to get rid of the fraction, the 2, multiply each side by 2. Okay. If you want to do that, fine. You don't have to. Let's look at another one. Let's get this up. Let's say this is our balanced reaction. Well, let's take 1 divided by each of those. And then we can write that rate, negative for the reactants, positive for the products, like this. Any questions so far?
No, I got you.
Okay.
I'm just trying to write this down.
Do what?
I'm just writing it down right now.
Okay. Now, if you did want to go back and use whole numbers, this one becomes a little more tricky, and you got a common denominator of 12, and it becomes -3 plus 12 plus 2. They'll accept if you write it that way. I wouldn't bother. I would write it fractionally. Don't do more work than you need to do. Okay, that's page 5. So feel free to go over any of this as much as you need to. Any questions before I have you do one, though?
No, I understand.
Okay, well then, do this next one.
Which one?
Oh, sorry, I didn't pull it down. Do that one.
Okay, so if it says relative, is that one like the initial?
Oh, I didn't mention that earlier. Well, maybe I did mention that earlier. That we're generally dealing with initial because it gets more complicated after that. I don't remember where I put it in my notes, but yes. And John, I see you're the only person here. I didn't realize somebody left. And I hope nobody's tried to join you. I didn't hear them or see them join.
All right, I got it.
Okay, I'll just write the answer here. Okay, any questions or maybe mistakes I made on that?
No, I got the same thing.
Good, okay. So now let's look at the differential again. We might get into some things that you know from calculus. A point here to make is this could be called the differential rate law, could be called the differential expression. They're the same thing. We had this a little bit in honors where I had you write the law or the expression, and then later you actually solve for something in it. We're going to do that today in the same respect. And just a note here, connecting this again back to equilibrium, when the rate forward is equal to the rate reverse, you are at equilibrium. Equilibrium does not mean there is no change. It means the change forward is equal to the change reverse. Well, we've got a method of doing this with the initial reaction rates. Let's see. Okay, I already said that. And this is the form that we would end up having with that. We've got K, which represents a constant, whatever that constant is, and it's different for different reactions and different conditions. So this has to be done typically experimentally. We've got a power, or I should say an exponent, technically called an order. We'll get to that later. And that could be written as we just wrote these up here previously, or not up there in the previous page previously, and just rewritten here. It's the same type of thing. Well, you said okay, but that didn't sound very confident, so let's do this. This is general, this isn't that specific one. So,
Oh, no, I've done this.
Okay, good.
Yeah.
Do remember, though, that this is lowercase.
Yeah.
Careful with capital as far as equilibrium or temperature Kelvin is concerned. We mentioned previous that a catalyst, again here over the arrow, can have an effect. So in that equation, the initial reaction rate could be written like this, where C is important. These orders or exponents up here, M, N, O, P, they didn't use O because maybe you could use that with 0. Use whatever you want when you're just writing the expression if they don't give you anything, but be careful not to write something that would confuse with a number unless it is actually the rate that you're determining.
Okay, and when we find the order of the reaction, do we need to count the catalyst's order as well? Or do we just the reactants?
Honestly, I've never done one with a catalyst.
If it was like 1, 1, 1, and it had an order of 3, but one of those was the catalyst, would we include that, or would we say it was 2?
I assume you would. I've never actually done one with a catalyst, and since I've never done one, I assume they wouldn't give that to you.
Okay.
But I would assume that you would. Okay, there's a mistake here. I should have made that a second line instead of an and. But if you've already done this, oh, and I mentioned to you in the conversation previously that these things have to be determined by experimentation. You can't just look at the graph and know the orders or the exponents. And orders, think of that like orders of magnitude, powers of 10.
Yeah.
Again, it can be 0. That's unusual, but in this class, we do kind of see that quite often just because it's easier. They give examples, but if you've done this before, it's probably not necessary order I just mentioned. Concentration rate. Okay, again, all of this determined by experiment, just to reiterate that. How should I do this? I should probably give you some examples, although you already know this, but because you might not know the next part. So let's look at this expression. So what does that mean? Do you know that yet?
What, the X?
Okay, I'll put it in words for you. The reaction is first order.
Yeah.
And if you write that, you're not getting any point. We've got to say something else.
With respect to A?
With respect to A.
I'll write that down.
Let's do a different example. And I think you've already got this part based on the example you gave me earlier. And I'm just making numbers up, although I didn't write them very clearly. That's a 2. So what is the overall for this?
I'd probably say the reaction is first order with respect to A, second order with respect to B, and third order with respect to C.
Those are all correct. But overall means the sum of all the exponents. So overall, this is 6.
6th order. Imagine that's pretty rare.
And that I don't think would ever, maybe even in reality, happen. Again, I just made those numbers up.
Maybe in a different universe.
Yeah, maybe. Okay. So let's go through the orders. So It says here just rate equals K, but as you're figuring this out, you probably would write something like this. What does that mean?
It's just 1.
It means it's 1. Anything raised to the 0 is 1. And we could plug that in a calculator if we needed to. I think you already know that, but in case other people need to. But anything to exponent of 0. First order is directly proportional to the concentration of the reactants. So what would first order look like? Well, we did it before with nuclear decay. So let's figure out what the rate is going to be. That's a blank question. If we, let's say, double whatever the thing is in first order, well, what happens to the rate? Well, it's directly proportional to, so the rate doubles.
That makes sense.
Okay. Well, let's look at another example. What if we triple the concentration with a first order? What happens?
Do a triple.
We triple the rate. Okay. Second order. Let's look at the same type of situation. Let's double the concentration in a second order. What happens there? Well, 2 to the second, 4 times. It quadruples.
Okay.
Okay. Another one real quick. Let's triple the concentration if it's a second order. What happens to the rate?
Be 6 times.
Well, be careful. That's a power, not a multiplier.
3 squared 9. Okay.
Okay.
That's what you did.
And that was mentioned over here. I don't know what the word is for that, like quadrupled or whatever. I'm not even going to guess. Probably. Fractional orders are rare, but do exist. You're probably not going to see that, but just know if you do that, they're maybe not trying to trick you. This is the way you need to write on the exam to relate these. It's what I referred to up here, when that if you didn't say the second part with respect to A, you wouldn't get any points. So be able to, for any of these, they're using that M and N from the expressions that they wrote somewhere higher up here. I forget where, maybe, yeah, previous page. But anyway, be able to write things like that. Oh, speaking of writing things, I forgot to mention this. For the second order, it could be written like this or like this. These are different situations, but this would be second order when we're dealing with A. This would be second order when we got A and B, but they're both ones individually. So you can't look at just one thing to determine what's necessarily going on in another thing. You've got to actually have your expression for whichever thing is going on. Okay. What do you think about this part?
Oh, I've seen these. I've
Okay.
done this in the Dingle book.
Okay, Dingle does a pretty good job of it. This is a thing that confuses a lot of people, though. I'm not going to read through all of this and do it word by word, but instead, let's see, I'll get read. If we were doing these in class, what I'd have is probably 3 or 4 people do different ones on the board to teach each other, because you might pick different things in figuring these out. But what I would always pick is something that's constant, so probably one of these 3 related to some change. So you could do these, but that change is going up by 0.25.
Yeah.
I'm probably going to choose this first one, this third one, because this is constant and this is doubling. And that's easier math for me to do in my head or on paper if I need to, than dealing with that other situation.
Yeah, for sure.
Okay, so let's deal with something constant. And again, you're probably going to get a table like this to figure out what's going on. I'm doing table logic. I'm not going to do the algebra, but it's in your packet if you want to read it. So comparing that, this doubles. I'm going to say 2x. Sorry, it looks like a T. Well, what happens with the rate when this occurs. So
Assuming
from here to
it's
here,
unaffected.
no change.
So it must be a 0, huh?
Hmm?
0 order.
So yes, okay. So for reactions 1 and 3, with respect to that,
With
we
respect to A,
have
yeah.
an equation that we could write like this to the 0 order. Okay. But that's not the whole thing yet. We've got another
Yeah, we got B.
another thing to deal with here. So let's look at B.
Yeah, let's
So
do 3 and 5.
3 and 5.
3 and 5. Oh, my bad. That's not constant. 4 and 5.
Yeah,
Okay, let's
you
see.
could do 4 and 5, but this isn't doubling or isn't changing in. I would do
You would do 1
these
and
two
4, huh? Yeah.
because that is 2 times. Now you can do any of them you want, but I would do that because that's 2 times, and this is constant. So we want one of these to be constant. Whichever side it is needs to be constant, and change the other one in some rate we can deal with. Okay. So now what we're really looking for is what is happening here. Well, it's not no change like before. It is a change. What is the change?
Yeah, it doubled.
It doubled. Okay, so between, let's see, this time we did 1 and 4. Between 1 and 4, the rate for B is first order.
Yep.
Because it doubled. And we could go back to, and when you're first doing these, go back and go through all the different processes as many times as you have to. But let's put it together. So now let's put in, okay, I should have had the K there, but let's put the K and let's put the A to 0. Almost didn't give myself room to that. Okay. So that is what we're looking at for the expression or the law based on that table. And again, this can only be done experimentally. If we were doing an experiment with this unit in class, I would have, although your class is small, if it's a bigger class, I might have 5 different groups of students. And they all should get the same K.
Yeah.
They should all get the same number, or at least very, very close to it, unless there's some problem. So much so that I might accuse people of cheating as I'm walking around the room before people catch on. Let's see, for people looking at this later, I probably should color code these. Okay, so we're probably going to, after having a question to ask for the expression or the law, have a question to solve for K. So let's do that. Let's rewrite this. And I'll use this. Well, can we simplify that? Oh, sorry, it's not on the screen. Can we simplify that? We don't have to. We can put this on the test and they'll accept it. But can it be written with any less writing?
Yeah, we could probably just neglect A.
Neglect A. Just put B, because A is not having any effect.
Mm-hmm.
Well, can we write that any simpler? Not a whole lot simpler, but you can do that.
Okay.
Because one's understood. It's one of those lazy chemist things I talked about in honors chemistry. But what is the overall for this?
It's first order.
Yeah, if we're looking at this, we'd say 0 plus 1, but you've already identified that we don't need that. So it's first order overall. And we'd need to write overall if we were having to write this out. So don't think with respect to something like we're doing in those previous ones. So what is K? Well, just in general, outside of this problem, what is lowercase k?
It's a rate constant.
Yes, a constant. Okay. So how are we going to find K for this?
We could look at the rate it gave us in that table, and then we could look at the concentration of B and solve for K.
Okay.
Correct.
Yes, we can. So we can take this and plug numbers in, basically. So K equals rate divided by B. All I did was rearrange, for those looking previously, this without the A in it because we identified that that wasn't needed. So did that little bit of algebra there. So now let's plug in some numbers. And I'm getting that from the table above, or maybe there would have been a previous question if it was on AP exam. And concentration from that table. B.
Okay.
Okay, I'm kind of running out of room here. But what about units?
I think M would cancel out. We'd be left with 1 over H.
1 over H, or H to the negative 1. Okay. And note that K can have any number of different units depending on the problem. That's one of its main things there, is to deal with those units. So we'll continue this over here. So calculator way of writing this, 0.5, second E, -2, divide by 2, or however you put it in the calculator. Just be sure you don't divide this -2 by 0.2. And you should get, actually I don't think calculators put that first 0. You should get a number like that, which means K is per hour, or again, you can write it as the inverse. Oh, wait, you let me write off the screen again.
That's all right. I know what you're doing.
Okay, and that's basically as far as I plan to go. I've already run over time. We'll briefly talk about some other things. There is a summary on this page, particularly people that aren't here that reviewing this later. Review over that. You may want to review over these several times. It might take a while for you to get the hang of this. At first, for a lot of people, it's difficult, but you'll eventually get it.
Gotcha.
Especially when we do more examples. Speaking of that, there is number 4 here. That is an example I'm not going to go through, but try to go through it on your own, marking the things as you're discuss them in your head or writing them on your paper and calculating them and see if you get the same answer. Again, though, you don't have to take the same things that they take.
Okay.
This is the ugly algebraic way. I've had students in the past that love this way and prefer to do it. I don't, but that's up to you.
Nah.
There's the one that you can work. I gave you the one that didn't have answers, but I can later give you answers to these or show my work for them if you need me to.
Okay.
Another one quite similar to that, just follows directly beyond the other one. Note that we got more things involved here as far as the reaction is concerned. I'm not going to get really into this now, but differential and integrated rate law are 2 things to cover next. I do want to mention part of that, though, for other people, and that is when you are doing these, you are going to either be given data tables, like we're talking about here, or you're going to be given graphs. If you're given graphs, they're not all going to look like this. You're going to get some curves and one straight line. Only one of these is going to be a straight line. If I go over this in the future, I'm not going to necessarily make you plug it in the calculator, but there is a way of putting it in the calculator and finding the R to find which is the closest to the straight line. You don't actually have to do that. You could zoom until you get a better idea. But I doubt they're going to require you to be putting things in a table in a calculator because of the time factor with this shortened test. So they're probably going to give you graphs or some idea about the graphs or ask you to explain the graphs. So if you have graphs, I don't have a pencil, and you had a curve here, and a straight line here, well, then you know it's second order. If you had a curve here, a straight line here, and a curve here, you're going to know it's first order. So whichever one gives you that straight line, that's which order your reaction is. And with these, it's concentration versus time, natural log, concentration versus time, and inverse concentration versus time. These are easy things to put in your calculator if you do have to graph them. And this is what they would look like. There's a tutorial here about how to put them in a calculator if you want to try that on your own and move forward. But I'm thinking a lot of this is going to go a little bit beyond